Hello, everyone, and welcome to PyData Global. We're excited to have you join us. Feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab, and we'll address them at the end of the session, given the amount of time we have left over. Now, it's my absolute pleasure to introduce Jen Wei. They'll be presenting a talk entitled, I Built a Transformer from Scratch. Jen Wei is an independent AI research engineer with a PhD in applied mathematics and a love for building things from scratch, especially when she probably shouldn't. She's reverse engineered transformer architectures, implemented modern techniques like mixture of experts and multi-head latent attention, and still enjoys writing clean PyTorch code at 2 a.m. for fun, and maybe for revenge. Jen currently works in the Gen AI space and shares her work openly on Hugging Face. Her favorite research topics include efficient LLM architecture, post-training techniques, and the existential crises of over-parameterized models. Now, please give it up for Jen.
Thank you, everyone. Hi, everyone. My name is Jen. So we all know how easy it is to type import transformers and get a model running. But we also know the pain that comes next when the loss explodes, when the inference latency is too high, or when you need to modify the architecture for a specific domain. And the black box suddenly became a black wall. That's where I live. I'm a full stack AI researcher with a background in applied math. My work isn't just about using those tools, it's about dismantling them. From reasoning-oriented reinforcement learning to distributed training system to optimizers like Neuron, I reverse engineering the magic to find the truth. Today, we're going to break open the black box. I've translated the original transformer paper into raw readable PyTorch code, so you can see exactly how the tensors flow, and more importantly, how to debug it when it breaks. I open source most of my work in Hugging Face Hub, and today's talk is based on my transformer from scratch tutorial. So for today, today's agenda, we will cover how the original transformer architecture works, how to translate each component into PyTorch. I will also walk you through the key ideas such as attention, masking, positional encoding, and feed-forward networks. Then I will walk you through a decoder-only forward pass step by step. Next, I will share some of the common implementation bugs and how to debugging them. Last but not least, we will cover where to go next, including code tutorials and training references. We have a lot to cover today, so if there isn't enough time to answer all your questions in the Q&A section, I will be joining you in one of the virtual tables afterwards. Okay, without further ado, let's get started. So what you are seeing is the transformer architecture. From the table, attention is all you need. To the left of the architecture is the encoder stack. To the right is the decoder stack, and each with 6 identical layers. So the role for encoder is to encode, meaning to comprehend. The role for the decoder is to decode, meaning to generate. And this is why encoder-only models like BERT are for classification questions. Decoder-only models like GPT and all your favorite Gen AI models are for generating tasks. And encoder-decoder models like BART are for sequence-to-sequence tasks, such as summarization, translation, and style transfer. So now, let's zoom in to see some of the key building blocks. At the bottom of the transformer architecture, you have the positional encoding, along with the embedding layer. And then we have the attention module. And last but not least is the feed-forward networks. So let's look at the size of each key modules. The feed-forward networks is actually the biggest in terms of its size. For the attention is all you need paper, its dimension is 2048, or 4 times the dimension of the hidden layer, the hidden dimension of the model. Attention module has dimensions 512 or D model. So I will talk about the number of heads and the heads later, but for now, you just need to know when you add all the dimension of the heads together, it equals to 512. Next comes to the embedding layer. Ultimately, it has to have the same dimension as the model's hidden dimension, which is 512. And I also want to point out the embedding layer is fundamentally different from linear projection or the neural network, the traditional neural network, in the sense that embedding is a lookup table. So what it does is it maps each token in your vocabulary into the embedding space, versus the linear layers are matrix multiplications. So that's the weight and bias. Okay, so now let's look at the positional encoding and embedding. As I mentioned, they are at the bottom of the transformer architecture. Why do we need positional encoding? This is because we need to have a way to inject the information of the relative or absolute positions of the token in the input sequence. Positional encoding is one way to encode those informations. These are their mathematical formulas, and I'm giving you a visual. So as you can see, they are just sine cosine curves and oscillating. To implement the bottom of the transformer architecture, we first pass the sequence length, the D model, and the batch size to the function that I defined called a positional encoding, which is essentially just implementations of those two math formulas that you see on the screen. And then we add the token embedding and the positional encoding together. We apply the layer norm to get the normalized sum. So that is the a plus sign inside a circle. And then we apply dropout to get the final output. So due to the time constraint, I won't have time to show you the code, but feel free to check it out in my transformer from scratch tutorial in the function create positional encoding. Okay, next up is the scale dot product attention, which is the classic attention mechanism. So you might want to ask, what is attention? Anyway, it's essentially just a function. It's a mapping that maps the input key, query, and value into some sort of output. And as you can see, Q, K, and V are at the bottom of the attention mechanism. And then you have some sort of output. All the inputs and outputs are vectors. So how do we compute the output? This is a formula. So let me explain what that is, what it actually does. So essentially, the output is the weighted sum of the values. The weighted sum, which is the softmax times V, where the weight assigned to each values is computed by a compatibility function of the query with its corresponding key. So the compatibility function comes from the fact that we are multiplying Q with the transpose of K matrix. The reason it gives us the compatibility is because, remember, Q, K, and V are all in the embedding space. So when you multiply two vectors in the embedding space, and if those two vectors are very similar, the product would be big. But if they are perpendicular, meaning their meanings are very different, when you multiply two perpendicular vectors, you'll get a 0. So this is why essentially QK would give you a heat map that tells the model where to look, and hence the compatibility. And I also want to point out that the value V is the crucial part, because there is a common misconception that KV are closely related than Q. But the reality is Q and K are closely related. V is its own entity. Why do I say that? Because based on, if you look at the formula, QK gives you the compatibility function, right? It tells the model where to look. But V is what value does the model have to retrieve. Okay, so now for the implementation. The first thing we could implement is this scalar. We do that by multiply Q to this 1 over square root of dk. Next is this compatibility function, which is just a PyTorch matrix multiplication. You just have to remember K needs to be transposed. Next, we add the attention matrix to the attention mask. And I will explain to you what is attention mask in a later slide. Now we apply softmax to the attention matrix, and we apply dropout to get the final attention score. At this point, attention score is the weight for the V, right? So if we recall, the output is computed as the weighted sum of the values. And then to finally get the weighted sum of the values, we just multiply the attention score to the V. And there you have it. That's how you get the attention output for the single head scaled dot product attention. So next, let's look at the multi-head attention. This is a diagram of multi-head attention. So essentially what it is we have a stack of single head attention that is processed simultaneously. And at the end, we concatenate the output of all single head attentions. And then we apply a linear projection to its final output space. Now, you might want to ask, why do we need multi-heads? Why not just one giant attention matrix? This is because mathematically, a single attention mechanism would average attention-weighted positions, as we have seen earlier. It's hard for the head to focus on two different things at the same time. But why multiple head would allow the model to focus on different aspects of the input sequence? The key is actually lies in the linear projection, because once we project the input sequence into several linear space, then we sort of gave the model different perspectives in each space. For the transformer model, we have 8 heads, which means 8 perspectives. And the dimension of each head is 64. So when you add all 8 heads together, you get the dimension of the model is 512. So in terms of implementation, instead of I understand the diagram looks like we have to define 8 linear transformations. But the trick is actually, instead of defining 8 linear transformations to a smaller space, which with the dimension 64, we actually define one set of linear transformation to the larger space, which is 512. And then we use this trick called tensor reshaping to reshape our tensor into the model times the number of heads. We reshape the D model into the number of heads times D head. This allows the model to capture different types of relationships, such as syntax versus semantics simultaneously, without exploding our computational cost. Next, we run the model through the scaled dot product attention we just discussed. And then we concatenate all the outputs. And then we run through the final linear projection to project the output into the output space. So one implementation detail, as you can see, when I initially did the tensor reshaping in the green box, I used the tensor.view. This is because tensor.view does not create another tensor. Instead, it returns a view of your original tensor, which means it's very memory efficient. However, in order to use tensor.view, you have to make sure your tensor is contiguous. And because we also use the transpose when we, for doing tensor reshaping, this breaks the contiguity of the tensor. So, and this is why when we are concatenating the output of all heads, we have to use, which is in this red box, we have to use tensor.contiguous.view. So the contiguity is very important for the implementation. All right, so you now have seen the single head attention and multi-head attention. So now let's talk about masking. Because if you ever had NANs or weird loss spikes, this is usually the culprit. We have two types of masks here. Both serves the same purpose, namely to masking out the tokens, which should not participate in the attention computations. So let's look at each of those masks. The first mask is the causal mask in self-attention. This is a visual of the causal mask. It is the time travel prevention. So we mask the upper diagonal. As you can see, they are all zero. The attention matrix are all zero, so that the model can peek at future tokens when predicting the next word. The second type of masking is called padding mask. It is for cross attention. And as you can see in the visual, notice the last two columns are zeroed out. That's because our input sequence could vary in length, and we want to pad the part that has no meaning, so that the model is not wasting its computational power to understand the padding, which has no meaning. And if we don't pad it, we're just introduce some noise to the context vector. Okay, so you have, so now let's move to the feed-forward networks, which is two linear transformations with a ReLU activation in between. And here's the formula, which is, the ReLU activation function is just the maximum of x and your first linear transformation. And then we convolve the output of the ReLU with your second linear transformation. So to implement the feed-forward networks, we first define two linear transformations. We then apply the ReLU activation function to the output of the first linear transformation. We then apply the second linear transformation to the output of the ReLU activation function. Okay, so you now have seen all the building blocks of the transformer architecture. So we're ready to do this a forward pass. So I will show you the decoder-only architecture, because this is the architecture for all the Gen AI models. So first of all, because we only have the decoder stack, there is no cross attention. Now let's start from the bottom of the stack. So we first have the shifted token, and then we feed the input sequence to the embedding and positional encoding stack. And then we pass the output into the masked self-attention. Here, remember, we're using the causal mask, which means don't peek at the future words. We then apply the residual and layer norm to the output of the masked multi-head attention. So we want to be careful with that. We are doing it in the order of residual and then layer norm. Then we pass through the feed-forward layer. Remember, this layer actually has a simpler structure, right? It's just two linear layers with a ReLU in between, but it has more expressive power because it actually has 4 times the dimension as the model dimension. Repeat 6 times. Last but not least, the prediction head, which is we pass a linear projection to get the legits and then apply softmax to get the probabilities for the next token, which is ultimately what we want to predict during pre-training. Okay, so at this point, the paper makes the transformers look elegant, but the implementation will absolutely fight you. This is why I hope my debugging tips will help you. So first of all, if something doesn't work 90% of the time, it's a shape mismatching or a masking issue. My second tip, scaling matters. Don't forget the square root of decay. My third tip, residuals first and then layer null. Wrong order will give you bad training. Next tip is attention score overflows easily, so use FP32 on legits. And trust me, if something looks wrong and you can't figure it out, it's a mask. It's always the mask. Next, where do we go from here? So for those of you who want a deeper dive, you can find my full implementation in Transformer from Scratch tutorial project on Hugging Face Hub. Or you can check out the annotated Transformer implementation from Harvard NLP. And if you want to look at how the Transformer looks like in production, you can check out the BART model in Hugging Face Transformer libraries. Or you can check out the OMO project from AI2. To wrap up, you've seen today that I don't just import those models. I dismantle and rebuild them. I apply the same first principles approach to my active research on distributed training and reasoning, like my current work on Neuron and Ray2 implementation. I'm currently looking for my next full-time principal engineer or R&D role. So if your team is moving beyond basic APIs and needs someone who understands the architecture deep enough to optimize performance, debug the impossible errors, and build custom solutions that actually scale, I'd love to chat. My work is all open source, so you can see the code for yourself. Please scan the QR code and let's connect. Okay, so this is the end of my presentation. So I'm ready to take your questions if there's any. Will we be able to get your slide? Absolutely. I can share with the host after this presentation. Okay, yes. Yeah, I can explain why the decoder side has to shift. So what happened is during pre-training, the goal is to predict the next token. So you shift the token to the right so that when you see the first token, you shift the token to the right. It's actually you add a starting token at the beginning of your input sequence. So when you predict, when you train the model, it's like you see the model sees the start token. It's trying to guess what is the first token of the actual input sequence. And then the next round, so let me give you this example. Okay, so let's just, So here I'm giving you, let's see, the quick brown fox jumps, right? So let's say the quick brown fox jumps is your input token. By shifting to the right, you're actually adding a starting token. So it's like a start, the quick brown fox jumps. So the model, the first round trying to predict the second round, the model trying to predict. The model sees so it tries to predict quick, and then brown fox jumps, etc. So this is why you want to shift the input sequence to the right, so that the model can see the start token. It's difficult to understand QK and V. It feels like the inner product of Q and K is compared to V. Am I having this right? If so, what is V? How is it calculated? Okay, so let me explain to you what are the QK and V. So the short answer is no, actually the V and K are compared together. Oh, I think I understand what is the confusion. Yeah, the second diagram is a little bit, the order was like reversed. The correct order is the scale dot product, where you have Q and K, and then the V is on the side. I think when you go to the multi-head attention, it doesn't really matter because the author had assumed you have, very familiar with this order. So no, in fact, Q and K are compared together, because if you look at the formula inside the softmax, it's Q times K transpose, right? So that's what I meant by they're comparing, because you are multiplying the vector Q to the vector of K, which is, if those two vectors are very similar, then the product would be like actually the length, the norm of those two vectors. But if they are very different in the embedding space, so what does like two different token looks like in a embedding space? It just looks like those two vectors are perpendicular. And if you multiply two vectors perpendicular, even if it's just in 2D, you will get a 0. So that's the meaning. And that's why Q and K are compared. So what does this V do? V are not compared with anything. V is, think about V as some sort of information you want to ultimately retrieve. The whole purpose of having the softmax or Q times K is to tell the model where or which information to retrieve. Remember, ultimately, we are having this attention matrix, right? So if the value on this heat map is high, then the model is looking at this particular location, and it will retrieve the V that is corresponding to that location. But V is actually what you want to retrieve, and Q and K is how you figure out where to retrieve the information. Does that make sense? Okay, I'm glad. Yeah, I probably went a little bit faster because we really can dig a lot deeper on this topic. So yeah, thank you for your questions.